Claude Opus 5 launched into a wall of benchmark videos, website builds, and game clone demos. But Unreal developers should ask a harder question. Can the model enter a project that already compiles, find a failure hidden across editor state, runtime behavior, and packaging, then prove it fixed the root cause? This is the Unreal debugging gauntlet I would run before trusting Opus 5 with a production game. It uses 3 real failure patterns, 5 evidence gates, and 1 rule. A confident answer is worth nothing unless the project agrees. The launch window is moving fast. In the public YouTube results I checked, a 4-minute Opus 5 breakdown reached about 61,000 views in 13 hours. A 12-minute analysis reached 40,000 in 9 hours, while a 36-minute hands-on test reached 17,000 in 6 hours. That is roughly 4,600, 4,400, and 2,800 views per hour at the moment of observation. The common pattern is speed plus a concrete test. Generic launch summaries are already crowded, so a late copy of the benchmark story has very little reason to exist. Anthropic's July 24 announcement gives us a more useful angle than raw hype. It says Opus 5 more than doubles Opus 4.8 on Frontier Bench at a lower cost per task. At maximum effort on Cursor Bench, it comes within 0.5% of Fable 5's peak at half the cost per task. The company also emphasizes verification, careful iteration, root cause fixes, and long-running multi-step work. Pricing remains $5 per million input tokens and $25 per million output tokens. These are official claims, not an Unreal benchmark, but they describe exactly the behaviors a difficult Unreal repair needs. The search gap is surprisingly clean. Searching Claude Opus 5 plus Unreal Engine still surfaces broad Opus reviews, a new Blender test, and older Claude and Unreal videos. 1-month-old Unreal integration video has around 120,000 views, proving that the engine audience is there, but it does not test Opus 5. The new Opus 5 Blender video I observed had only a few hundred views after 6 hours. In other words, the topic is hot, the Unreal audience exists, and the exact intersection is not yet saturated. The opportunity is not another city generation montage. It is a credible, evidence-first debugging story. A blank level challenge mostly rewards visual speed. A debugging challenge measures judgment. In Unreal, the source code can look correct while a blueprint overrides the value after begin play. The editor can load an asset that the packaged build never cooks. A simulation can look stable at 60 frames per second, then drift when the frame rate changes. The model must trace state across systems, change the smallest responsible layer, and rerun the same evidence. This is where an agent either behaves like a careful engineer or becomes a very articulate random patch generator. Test 1 is a visual trap. The packaged game's interface is sharp, but the 3-dimensional world is soft. A startup command appears to set full resolution, so a shallow agent keeps rewriting launch flags. The real task is to follow the state after level load. In this failure pattern, gameplay logic can query an upscaler's preferred screen percentage and execute a new console value later, overriding the command that looked correct at startup. A passing repair must identify the later writer, explain why the UI stayed sharp, change the responsible project logic, and verify the same camera before and after packaging. Test 2 is an asset lifecycle trap. The object resolves in the editor, but a packaged build shows a placeholder. The tempting fix is a synchronous load or a hard-coded delay. That can hide the symptom while keeping the cook problem. The model should inspect the soft object path, verify whether the asset is actually referenced for cooking, keep the asynchronous completion path safe, and distinguish an unresolved asset from a slow one. The pass is not a screenshot from the editor. The pass is the packaged executable loading the intended asset, logging the resolved path, and reusing the cached result without a stall. Test 3 attacks a favorite illusion. It looked right on my machine. The variable step simulation seems fine at a stable frame rate, then diverges when frame times arrive in uneven chunks. A good agent has to separate rendering time from simulation time, implement a bounded accumulator, clamp runaway catch-up, and compare against an analytic reference. Then it must rerun the test with deliberately irregular frame chunks. In this real-unreal capture, the variable path accumulates large error, while the fixed one stays close to the reference. That is the kind of measurable proof a coding benchmark rarely shows. Each Gauntlet task uses the same 5 gates. First, compile the exact target with no hidden editor hot reload state. Second, reopen the project and verify the saved asset or configuration. Third, run play an editor or a deterministic automation map. Fourth, build the packaged artifact and execute it outside the editor. Fifth, collect a fixed camera frame plus narrow logs that prove the expected event and show no new blocker. If a model fixes gate 3 but breaks gate 4, the score is not 4 out of 5. The repair failed. This all-or-nothing rule prevents attractive partial demos from becoming false success stories. The scorecard rewards engineering behavior, not typing volume. 30 points go to locating the first responsible layer. 25 go to a minimal patch that preserves project intent. 20 go to independent verification, 15 to recovery after the first failed attempt, and 10 to a clear handoff that separates confirmed facts from assumptions. I would subtract points for unrelated refactors, deleting safeguards, claiming success before packaging, or replacing an asynchronous design with a blocking shortcut. This makes a slower, careful run beat a flashy one-shot generation if the flashy run cannot survive reality. The initial instructions should be strict. Reproduce the failure first. Name the last successful stage and the first failing stage. Propose one hypothesis at a time. Before editing, list the exact files and runtime state that support the hypothesis. Make the smallest reversible change. Then rerun the same validation and report what remains unproven. That prompt does not make the model smarter. It makes the evaluation honest. It also mirrors how a human reviewer can audit the run without trusting hidden reasoning or a celebratory summary. My launch day verdict is simple. Opus 5's official strengths line up with the difficult part of Unreal work: long context, root cause debugging, verification, and careful iteration. The YouTube demand is already visible, and the Opus 5 plus Unreal search gap is still open. But there is no honest Unreal verdict until a real run passes compile, editor, runtime, package, and evidence gates. So do not begin by asking it to generate a city. Give it a project that almost works, keep every failure in the video, and see whether it can earn the final green check. That is the Opus 5 test worth watching.